The Kim SJC, right, sir? I have done it.
No.
The official
Official
SJC.
backend check. Yeah.
Okay, sir.
Hi, Sarina, you there?
Yes, I'm here. Can you hear me?
Yes,
Yeah.
yes, clear,
Great.
crystal clear. Yeah.
Great.
So
So
another,
we have just 3 minutes left.
yeah.
Okay, perfect.
Hi, Sarina, you there?
Shall I show Dr. Ronald, sir. Shall I pin you, sir, now?
Not now, not now. Oh, exactly at 4:30.
Okay, sir.
We are going to start exactly at 4:30.
Somebody's YouTube is on.
Yeah, they have to mute it.
Yeah, I hope it won't interfere. Jayashree,
I
Not
think
mine, ma'am. Not mine.
not yours. Huh?
one of our whoever it is, our department.
Maybe they can mute it.
Yeah, they have to. Can you just put it on the chat box?
A chat box, or we may have to announce. If anybody has kept both your laptop and YouTube on, please turn off your YouTube. The sound will get. No, it will affect only if Suhas or Jay.
Yeah, someone has to mute themselves.
Yes,
That
somebody
is,
has to mute themselves. I don't know.
find out whether Suhas has he kept it
Some
on.
Joshua, John, Anthony, somebody.
Is there in
Joshua,
our
John. Yes,
Joshua?
it
How
is.
come he is there in our
I don't know. It is come
Zoom?
in the participant.
Oh,
Yes,
4:30,
sir.
sir.
It is
Exactly.
there.
Yeah, just pin me. We'll start.
So is it
Professor
okay?
Serena, we are going to start. Professor
Over
Serena,
to over to you, sir. Dr. Ronald, sir. Over to you.
yeah.
Yeah,
Can I
okay,
share the
so
slide?
go ahead. I'll
Yes.
mute myself for you. Okay.
Yeah. Yes. Sunita, please share the slide so that Ronald sir can introduce.
Okay. Ladies and gentlemen, good evening. On behalf of Reverend Father Dr. Victor Lobo SJ, the principal of St. Joseph's College, Bangalore, and the Department of Chemistry, I, Ronald Mascarenhas, from the Department of Chemistry, extend a cordial welcome to all the participants of the seminar from India and across the globe. We are happy and excited about your response to this webinar. We are using Zoom platform for this webinar, and it's live streamed on YouTube. I'm glad to introduce the resource person of the day, Professor Serena DeBree, an American scientist. Professor Serena DeBree studied at Southwestern University, Georgetown, Texas, USA, where she completed her bachelor's program in chemical sciences in 1995. She received a doctorate from Stanford University in 2002. She then moved to SLAC, National Accelerator Laboratory, where she worked first as a beamline scientist between 2001 and 2003 at the Stanford Synchrotron Radiation Laboratory, and later as staff scientist between 2003 and 2009. In the fall of 2009, she relocated to Cornell University in New York, where she accepted a faculty position as assistant professor at the Department of Chemistry and Chemical Biology. In the summer of 2011, she moved to Germany and started to work as a W2 professor and research group leader at the Max Planck Institute of Bioinorganic Chemistry, and since 2012, Max Planck Institute for Chemical Energy Conversion, MPI, in Germany. Since 2012, she has held the position of an adjunct professor at Cornell University, as well as a honorary faculty position at Ruhr University, Bochum, since 2014. Professor Serena headed the research group X-ray spectroscopy at MPI CEC until 2017, when she was appointed the director at this institute and promoted to a W3 professor cadre. To be promoted as MPI director and to be at the helm would be a dream for any scientist. She had the privilege to be raised to this position in the year 2017. Currently, she leads the Department of Inorganic Spectroscopy at MPI CEC. Additionally, she is the group leader of the PINK Beamline project at the Energy and Materials Institute Laboratory at the Helmholtz-Zentrum, Berlin, Germany. Her expertise lies in the application and development of X-ray based spectroscopic methods as probes of electronic structure in biological and chemical catalysis. Research in her group focuses on answering fundamental questions in energy research, namely, how does one reversibly store and release energy from chemical bonds using earth-abundant transition metals, and how is this done most efficiently? Her research group studies homogeneous, heterogeneous, and biological catalysts to answer these questions, with a primary focus on enzymatic catalysis. She is an expert in the application of advanced X-ray spectroscopy to understand catalytic transformations. She has a large research group with several postdocs and research students working with her. Currently, she has 7 postdoctoral researchers and 7 PhD students in her group. She has won several awards. To mention a few, European Research Council Synergy Grant for the project Unraveling the Secrets of Copper-Based Catalyst for CH Activation, collaborative project with researchers from the University of Oslo, Norway, Norwegian University of Life Sciences, and University of Turin, Italy. She is the Associate Editor for Chemical Sciences since 2018. In 2016, she received Inorganic Chemistry Lectureship Award. In 2015, Society of Biological Inorganic Chemistry Early Career Award. European Research Council Consolidator Grant for the project Spectroscopic Studies for Nitrogen Reduction from Biological to Heterogeneous Catalysis in 2013. Kavli Fellow US National Academy Sciences Award in 2012. Alfred P. Sloan Research Fellow between 2011 and 2013. On behalf of the principals in Joseph's College, Bangalore, Father Dr. Victor Lobo SJ, and the Department of Chemistry, along with all the participants of the webinar, first of all, I would like to thank you, dear Professor Serena, for accepting our invitation and extend a very warm welcome to you. Ladies and gentlemen, please mute your microphones and type questions in the chat box. The questions will be taken up at the end of the session. Please indicate your name and the name of the organization. So, ladies and gentlemen, over to Professor Serena to deliver a lecture on the topic X-ray spectroscopy to understand processes in biological catalysis. Thank you.
Okay, thank you for the kind introduction, and thank all of you for being here, albeit virtually. I guess the fun part about the coronavirus lockdown is I think I've got to travel even more of the world than I usually do, and most of it from the inside of my office. So let me start by sharing my screen and making sure that everyone can see this. So can everyone see this okay?
Yeah.
Yes, yes.
Great. Okay, thank you. So as you heard from the very nice and detailed introduction, my area of specialty is in X-ray spectroscopy. And I'm particularly interested in taking the tools that have largely been developed by the physics community and translating these two important problems in both chemistry and biology. And today I'm going to focus specifically on the part of my group that focuses on biological catalysis. But before I even start talking about the research part of this, I want to begin by thanking all of my group members. This is now a somewhat dated picture because, like many people, we haven't been able to have these large gatherings anytime recently. But this was the last picture we took in Mülheim, and I'm incredibly fortunate to work with a very talented group of PhD students, postdocs, as well as undergraduates, master's students, technical staff, and group leaders. At the time of this photo, these were the flags that represented the different nationalities of the group. I think we would have even more to add because it's a very diverse and international group, which makes, I think, life really fun and interesting. But we're not just diverse in terms of the different nationalities we represent, but we're also really a diverse group of scientists. And so I hope that for all of you, regardless of what your background is, I suspect there is at least a part of this talk that you can connect to, because in order to realize the research that we do in my group, we really merge what we learn from physics and chemistry and biology. And we also even require expertise in engineering. So we do everything from instrumentation development to try to do new kinds of spectroscopy to computational studies to try to understand the spectroscopy. But we're also busy making molecules or isolating proteins, and then doing challenging spectroscopic measurements both in the laboratory and at synchrotron facilities. And so I want to tell you how all of these different subject areas really come together to start to solve some challenging questions, especially in biology. But before I get to the focus of today's talk specifically, I want to talk about some of the sort of key reactions that our institute as a whole is interested in. And so as you heard, I'm at the Max Planck Institute for Chemical Energy Conversion. And sort of the fundamental question we have at our institute is, how can sustainable earth-abundant metals enable the activation of strong chemical bonds? Because if you think about energy research, ultimately what we'd like to do is know, how can I most efficiently store energy in a chemical bond and then release it, right? And as chemists, we all know that there's kinetic barriers to affecting these conversions. And in general, that means we require some sort of catalyst to lower that barrier and make these conversions more facile. And that catalyst could be a heterogeneous catalyst on a surface. It could be a homogeneous catalyst that a chemist makes in the laboratory, or it could be a biological catalyst found in a naturally occurring enzyme, or perhaps even a synthetic enzyme. But the question that our institute asks, what do all of these catalytic processes have in common? If I'm interested in knowing how I split the triple bond in nitrogen and how I do that most efficiently, it's our belief that we need to understand how that happens in different catalytic limits. And so ultimately what we're interested in is understanding an atomic level understanding of how these transformations occur. Okay? And we're interested in understanding things like N2 reduction, proton reduction, water oxidation, CO2 reduction, and methane oxidation. So these are some of the primary energy conversion reactions that my group focuses on. But today we're just going to look at a subset of them just so I can kind of tell you hopefully a somewhat pedagogical story as well about the kind of chemistry we're interested in. And so today the two reactions I'm going to focus on are nitrogen reduction and methane oxidation. And so nitrogen reduction, as the chemists in the audience will know well, takes 6 protons and 6 electrons to reduce the triple bond in nitrogen and produce 2 molecules of ammonia. And in nature, this occurs using the enzyme nitrogenase, and I'm showing just a small part of this protein. This is its catalytic active site that contains both molybdenum and iron, and we're going to talk about this more later. And the other reaction we're going to talk about is methane oxidation that takes methane and oxygen to methanol. And this is largely done by a family of enzymes called methane monooxygenases. And these can use either iron or copper. But what you'll notice is that for both of these enzymes, they're using earth-abundant metals. And that's often in contrast to what chemists might use in a laboratory. And so these are also sustainable processes in that regard. And we'd like to better understand how earth-abundant metals carry out difficult chemical transformations. And so in my group, the way we do that is largely to employ X-ray spectroscopic methods. And so as some of you may know, if you need a really intense source of X-rays, then often experimentalists go to synchrotrons. And now worldwide, there's about 60 synchrotrons in the world. And at all of these facilities, you accelerate electrons to near the speed of light. And as they round the curves of this circle, that change in acceleration basically results in the production of intense radiation. And this is the radiation that we use to do a wide range of experiments, like X-ray absorption spectroscopy, X-ray emission spectroscopy, two-dimensional X-ray spectroscopies that are known as resonant X-ray emission or resonant inelastic X-ray scattering, X-ray magnetic circular dichroism, and nuclear resonance vibrational spectroscopy. Now, don't worry about it. You don't have to remember all of these acronyms. I'm going to come back to them as we use each technique. And I think in my talk today, 4 of these techniques will appear. I won't talk about any NRVS for the projects that I'm talking about today. But one of the things I want to emphasize is we're using these synchrotron-based methods, and that sometimes means that it's not as broadly applicable for many of you. You might think, I'm never going to use synchrotron radiation in my research. But one thing I want to point out, especially for some of the younger people who might be listening, is there's been a lot of developments in recent years in bringing X-ray spectroscopy in-house. And so at our institute in Mülheim, we actually now have 2 instruments to do in-house measurements. And although these aren't sensitive enough for very dilute biological samples, they work quite well for more concentrated catalytic materials, especially for some of the heterogeneous catalysts we study. And so that's something to keep in mind. I think that many of these techniques evolve with time, and through the course of your own careers, you may see they actually become much more accessible and much more relevant to your own research. So as I already said, we're interested in all these methods. We're also interested in ways to get two-dimensional spectroscopy, mainly to improve selectivity, and I'll talk to you a little bit more about that later. An important part for us is to also take all of these methods and correlate them to computations in order to maximize the insight we can get out of the spectroscopic measurements, and then actually to apply all of these methods to real systems. So let's talk about the first real system that we're going to talk about today. And this is the nitrogenase sort of family of enzymes that I already referenced. And I'm going to focus today just on the most common nitrogenases. These are the so-called molybdenum-dependent nitrogenases. Okay? And molybdenum-dependent nitrogenases carry out the reaction that I'm showing here. So they reduce nitrogen to ammonia, but what you'll notice is the stoichiometry looks a little bit different than what we saw on the slide before. So now we need, instead of 6 electrons and 6 protons, we require 8 electrons and 8 protons. So we actually produce an obligate molecule of H2. And this is actually thought to be mechanistically important in the enzyme's mechanism, which is something I would be happy to discuss more with you during the Q&A. Another thing you'll notice in this reaction is that it requires ATP to drive the reaction. And so one thing I want to be clear on, a lot of times when bio and organic chemists talk, they sort of imply that nature is better than what we're doing in heterogeneous catalysis, and that's not always true. One has to be careful here. 16 molecules of ATP is actually a fair amount of energy. And if you look at the energetics of nitrogenase reduction are actually not so different than the energy input requirements of Haber-Bosch, which uses high temperatures and high pressures. So what we know is that these are reactions that operate at fundamentally very different thermodynamic limits, but they both require significant energy input to drive this reaction. And that's not surprising. This is a pretty challenging conversion. So the way nature does it is it hydrolyzes ATP to provide the energy to drive this reaction. And it does this at something known as the iron protein. This is the native reductase of the molybdenum-dependent nitrogenases. And it contains a 4-iron 4-sulfur cluster. And so this iron protein needs to associate with this catalytic MOFI protein. This is a 250 kilodalton protein. And within this 250 kilodalton protein, you have another iron sulfur cluster. This is an 8-iron 8-sulfur cluster. And then you have that catalytic FeMoCo active site I already talked about. And so what you need to do is then drive the transfer of 8 electrons as well as 8 protons 8 times in order to complete this process and get the 2 molecules of ammonia. And I think it's helpful to look at this catalytic 250 kilodalton protein in a little bit more detail. And so this is a large protein, but we're quite interested in the inorganic active sites that are buried in it. As I said, we're in the Department of Inorganic Spectroscopy, and so we're focused a little bit more on the inorganic cofactors inside. And what you can see here, and this is something that for me as a chemist is really fascinating, these are 2 different metal clusters that biology goes to great lengths to actually biosynthesize. One of them is this 8-iron 8-sulfur cluster that I mentioned. It's the P cluster. And the P cluster's job is just to shuttle electrons. It doesn't do any catalysis. But then somewhere else in this protein, you have the catalytic active site. This is the so-called FeMoCo. So now instead of 8 irons and 8 sulfurs, you can see this cluster looks a bit different. Instead, it has 7 irons, a capping molybdenum, a carbon in the middle. The molybdenum is coordinated by homocitrate, and then the other iron is coordinated to the protein just by this cysteine. There's also a histidine coordinating on this molybdenum side that's not shown in this diagram. But for me as a chemist, what fascinates me is how is this transformation actually dictating the difference in the electronic structure properties of this cofactor, and how does that enable this cofactor to carry out one of the hardest reactions in chemistry, right? So there's something really kind of beautiful about the way that nature has engineered this. And this isn't something we're going to talk about today, but for me, the biosynthesis of iron sulfur clusters is really fascinating. And I will tell you that there are specific genes we now know and understand. Their sole purpose is to generate the proteins that then subsequently allow for the insertion of this carbide. So it seems rather intentional from a biological perspective, and that's something we yet to fully understand from a chemical perspective why that happens, okay? But what you can see is we're looking at small details. We're looking at why did nature make a single atom substitution in order to make this active site a better catalyst. And ultimately, what we want to understand is how this active site transforms at every stage of the catalytic cycle, okay? We also want to know how the whole protein plays a role and how the reductase plays a role. But first things first, we want to actually answer what's happening at this active site, okay? So this protein, when I isolate it in a lab and it's in its resting form, we call that state of the MOFI protein E0. That's its resting form. When we put in 1 electron and 1 proton, we reach E1. And I told you we need to do this 8 times, so we'll have subsequent other E sub n states all the way E1 through E8, okay? And what I'd like to know is at every stage, where does the proton go? Where does the electron go? But of course, the first questions that we had when we started this, and so this talk will be somewhat historical, is what is the full atomic composition of this cluster? And then when I know the atomic composition, what's the charge distribution? How is the oxidation state distributed? So for the inorganic chemists in the room, these are all open shell metal ions, right? The irons are iron 2 or 3, so they have 5 or 6 electrons. We also have an open shell molybdenum. How are these electrons distributed, and how do they couple with each other? How do I think about the magnetics of this, right? So this is something that is complicated on so many levels. And what I want to tell you about today is just a small part of this story. Biologists and chemists have been studying nitrogenes for decades and decades now. And I just want to tell you a small part of the story, and that's the role of X-ray spectroscopy. And I'm going to, not surprisingly, focus on my own group's contributions, but I will say that there were many people before us who also made contributions that have really shaped our understanding of this. But I'm going to sort of come into this story in light of my own scientific career, because for the younger people who are listening, maybe it provides some inspiration into how you might find your own way in research and think about finding your own research projects. And so what I already told you that this cofactor, it has a carbide in the middle. And the question is how did we even figure out that was a carbide in the middle? And so I want to start you just with this picture of what this cofactor actually looked like in 1992. And so in 1992, I was an undergraduate, and I was already quite interested in bio and organic chemistry. And this structure came out, and it had no carbon in the middle at all. And so if you look at the irons, they're all 3-coordinate. And this is exactly what you would teach your undergraduate inorganic chemistry students, something that doesn't happen, right? And so this already was quite surprising. It actually inspired chemists to try to do low valent iron coordination chemistry, which in fact has opened up really exciting areas of research that we hadn't thought about before. However, its exact relevance to catalysis and FeMoco is still a bit of a question mark, because a decade later, this seemingly empty cavity with a higher resolution structure now had a light atom inside it. And they needed a high enough resolution crystal structure to find that, right? Because you have all these heavy atoms that are contributing the bulk of your electron density, and finding a light atom in there from crystallography, very hard, okay? And so initially, the researchers speculated that the central atom might be a nitrogen, so a nitride. And they actually liked the idea that perhaps the protein somehow self-assembled by turning over. So cool idea, right? It was, though, however, later, as you know now, found not to be the case. But I wanted to just give you a history of sometimes how hard it is even to just identify an atom, right? These are challenging questions for us as scientists. And so after this crystal structure was reported with a light atom, that the authors clearly said, it could be carbide, nitride, or oxide. They liked this idea that nitrogen was incorporated during turnover, but they couldn't say for sure. And so worldwide, people tried to solve this problem. They did fancy EPR experiments, in particular with lead efforts from Northwestern and Brian Hoffman's group. They did Endor and ESOM, where they said it's not an exchangeable nitrogen. Later, they said it wasn't a nitrogen, whereas DFT studies favored a nitrogen. Eventually, the spectroscopists and computational chemists got together, and they said it wasn't carbon or nitrogen unless that central atom just was not magnetically coupled to everything else. But there were QMM studies that favored a carbon, and NRVS and XF studies that said their data were consistent with a light atom, but they couldn't identify it. And there were also other DFT studies that favored a carbon. And so this was actually at the time when I was starting as an assistant professor. I'd spent a lot of time at SSRL learning things from really brilliant physicists, in particular from Uwe Bergman. And I learned a lot about valence to core X-ray emission, but it hadn't really been used at that time that much in chemistry. And so as I was starting my own independent career, I asked the question, well, maybe valence to core XES could help us solve this puzzle. And it's a challenging puzzle that a lot of methods can't solve. And in part, it's hard for the X-ray crystallography or for any scattering-based method, because we're trying to identify one light atom out of tens of thousands of light atoms, right? So what's the selectivity of this valence to core X-ray emission I'm talking about, and why might it be helpful? And so for this, I just want to explain to you briefly what X-ray emission is in general. So X-ray emission is largely an element selective probe, and it's because we're ionizing core electrons. So because we're thinking about FeMoco, and we know that this central atom is bound to 6 irons, what I want to think about is having selectivity around the iron. And what I'm going to do is this is my iron simplified energy level diagram. What I want to do is ionize a 1s electron from iron. And I do that by just sitting at 8,000 electron volts so that this has a high absorption cross-section and the probability of this event is very high. Then what I want to do is watch all of the processes that follow after I create a core hole. And so the most likely event is that an electron in a higher level refills that core hole. And this would be a dipole allowed 2p to 1s process that results in the k-alpha lines that are going to be just split by 2p spin orbit coupling. Okay, so not a whole lot of chemical information in there. It can help you get a higher resolution X-ray absorption, and we'll talk about that later. But this is not necessarily the most informative region, chemically speaking. The next most likely event are the so-called K-beta lines. These result from 3p to 1s de-excitations and the fluorescence that results. And they're going to be split by 3p 3d exchange. This means it's a nice spin state marker. It's sensitive to how many unpaired electrons I have on the iron. And it can even allow you to do sort of spin and oxidation state selective X-ray absorption, which is pretty cool. But the method I want to talk to you about is the least likely event to happen, and that is the very small probability that electrons in filled valence orbitals refill the 1s core hole on the metal. This is the so-called valence to core X-ray emission, and because it's coming largely from filled ligand-based orbitals, it's highly sensitive to the ligand ionization energies, okay? And in other experiments, we've also showed it can even enable ligand selective X-ray absorption, which is also pretty interesting. But let's just talk about just how we use this for nitrogenase. So I already told you that in valence emission, I have electrons in filled ligand orbitals that refill a core hole on the metal. So for instance, if oxygen is coordinated, I would see this weak oxygen 2s to iron 1s feature. If it's nitrogen coordinated, it would move up in energy. And if it's carbon coordinated, which is what we saw in MOFI, it should appear at even higher energy. And that's exactly what we observed in the protein. So this provided the first empirical evidence that perhaps this was a central carbide. But we also wanted to calculate this. And so we did this using a simple DFT protocol. And in order to really emphasize the contribution of the carbon, we measured both the P cluster that I showed you, that 8 iron cluster that had no light atom, and we subtracted it from FeMoco. So this gave us this experimental difference spectra that gave us a way to sort of emphasize the contribution of that light atom. And then in the computer, we can put any atom we want here and do the same subtraction. And what you can see is that it only really agreed when it was carbon, and both nitrogen and oxygen were way off. And so this was now nearly a decade ago, late in 2011, so I guess, yeah, 9 years ago now that we showed this. And in the time that's followed, we've also come to understand exactly how this carbide gets in there. And we also start to have ideas of what it's actually doing in there. But what I want to do is sort of take you through this just stepwise to keep this talk sort of pedagogical. So as I told you, we figured out that this was a carbon, but now the question is, well, what is even the charge on this cluster? And for those of you who are maybe molecular chemists, not knowing the charge always seems strange, right? Because you could figure this out from how many counter ions you co-crystallize. But you have to keep in mind, this is a 250 kilodalton protein. And so this means that it's very hard for me to know the exact charge. What I do know is the total spin. So this is an S equals 3/2 cluster based on EPR. But based on that spin, you can actually support cluster charges that range from 1+ to 3-. So these vary by 4 electrons. And if you think about that, I told you I need 8 electrons to complete the whole cycle. So in effect, I don't know if my start point is at the beginning or halfway through my cycle. That's sort of how far off we were at one point in knowing what the charge distribution was. What I'm showing here, though, are the charge distributions that were proposed in the literature. So they went from largely iron 3 to largely iron 2, and yet they always assumed the molybdenum here was molybdenum 4. And so again, we wanted to go back to the literature and ask just the simple question, why did people even think this was molybdenum-4? And this is something I always really emphasize with my students, is it's so important really to track back in history and ask, why do we make the assumptions that we make? And what we found actually when we looked back in the literature is it was way back in the mid-1970s that Kramer and Hodgson proposed actually that this cluster contained molybdenum-5. In follow-up studies, though, they actually said it was molybdenum-3 or 4 based on bond distances from XAFs. And it turned out that this initial study may have been actually oxidized protein. In the mid-80s, based on 95 molybdenum Endor, there were researchers who said that molybdenum-4 was most plausible, but they also said the coupling was so complicated they couldn't say for sure, right? And then interestingly, in the late 80s, based on molybdenum alloges, Hedman and Hodgson reported that the data looked like molybdenum-3 or 4, but in light of the Endor, they said molybdenum-4 was most probable. And so if you actually look at two of these papers, both authors at this time were still saying 3 or 4 were possible. But somehow, after these papers where molybdenum-4 appeared only in the abstract, it kind of appeared set in stone. And so we wanted to just revisit this, and this is work that was done by Ragnar Bjornsson and Fred Lima, both former group members of mine, who published this work now in 2014. And so what they did was the opposite experiment of what I'm telling you about. I told you about X-ray emission, where you have electrons in filled orbitals refilling a core hole on the metal. They instead did X-ray absorption. So they are now probing the unoccupied orbitals and virtual levels. But they didn't want to do the same experiment that was done by previous researchers in this field. They wanted to do a more advanced experiment. And interestingly, although it was already in 1991 that K.O. Hämäläinen from Helsinki showed you could get much higher resolution X-ray absorption spectra by measuring K-alpha detected, or high energy resolution fluorescence detection. It hadn't actually been applied to biological systems yet. And so let me just sort of show you here. An X-ray absorption spectrum looks at the modulation in the absorption coefficient as a function of energy. So for instance, if this is an iron edge, I'm sitting on some strong scattered background, and then I have this sharp discontinuity, which is the so-called edge, that results when I have a 1s core ionization. Now, X-ray absorption is a bit of a misnomer because for dilute systems, we rarely measure true absorption. What we actually typically do is to assume that the absorption is proportional to all the events, secondary events that follow, right? So when I ionize that core electron, I will have some scattering, but I'll also have this K-alpha and K-beta emission that I already told you about. And so what I'm sitting here on top of is all of that scatter. If I have a good energy resolving detector, that means where I can set electronically a certain energetic window. So instead of taking everything, which I'm showing in the gray box, I focus only on, say, the K-alpha line, then I can reduce the scatter background. But intrinsically, the spectrum will look the same. Now, if I can use a Bragg optic, so something that can take an even narrower line than what we're able to do electronically, I look at just a subset of possible final states depending on the width of this window. And so what happens, instead of the spectrum being broadened over all possible final states, it starts to sharpen. And this is the so-called HERFT, which is an unfortunate acronym to pronounce, but this is high energy resolution fluorescence detection. Now, why do I care about this for something like molybdenum? Well, normally molybdenum is so high energy that it suffers really badly from core hole lifetime broadening. So typically, molybdenum spectra for a molybdenum model complex, shown here in red, is like this. And this is a corresponding molybdenum-3. You can see the edge just skates up, but it's entirely featureless. What's shown in blue are the HERFT spectra for the same compounds. And so you can see how the spectra sharpen. And particularly if you look at the first and second derivatives, especially for the molybdenum-3, you can start to see that it becomes much more featured. And now I care about this because if I want to quantify the electronic structure, if I want to correlate it to calculations, I've got to see something in my experiment, right? And so that's why we wanted to get these at higher resolution. And so that's what we did. And I'm just focusing on Fred's data in the pre-edge region. And I want to show you that he always measured the protein that's shown here in red in the experiment. And then he looks at model complexes that somehow relate. And so this is a molybdenum-5 model complex that's shown here in blue. And then the other complex he used is what we often refer to in our group as the home cubane. This was made by Dick Holm, a very famous inorganic chemist from Harvard. And this is a complex that we know from magnetic Mossbauer is formally molybdenum-3, okay? And that actually is shown here in black. Now, what's really quite nice here is that you can see when we calculate these pre-edges by theory, there's very nice agreement. And so that gives us hope that we can use this to understand the electronic structure. And what we see is both in this home cubane and in FeMoco itself, we actually have molybdenum-3. But not only do we have molybdenum-3, we have molybdenum-3 in this weird spin configuration, right? This is another thing we teach undergraduates doesn't happen, right? This is something known as a non-Hund configuration. And we believe that this spin flip happens because the molybdenum actually has bonding interactions with the iron that actually favor a certain spin orientation, right? And so that's kind of what I'm showing here, that you basically have a ferromagnetically coupled pair that is optimized to interact with the two down electrons, and then this isolated ferric site with opposite spin that interacts with this other pair. Now, of course, this is broken symmetry DFT. It's not reality. And so one can come back to the question later, is this what the electronic structure really looks like? And I'll get back to that. But the question is can we show this some way, not just in a computer, right? Because I think as an experimentalist, I'm always most satisfied when I can think about an experiment that allows me to access these challenging questions. And so what I already showed you were molybdenum K edges. These involved 1s ionizations at molybdenum. The other experiment we can do are molybdenum L edges. These are 2p to 3D transitions. And so here again, we actually looked at a series of molybdenum 3s. So FeMoco, which I told you we assigned as molybdenum 3. We looked again at the home model, and we looked at a regular molybdenum 3 that is 3 halves. So it's D3 with 3 spin-up electrons. And from the L edge, there's some differences in broadening and the width of the edge, but you can see that here at the maximum, they're all the same, and they're all consistent with molybdenum 3. So how can I tell if they're magnetically different? And the way you can do this is to do something called X-ray magnetic circular dichroism. And so what we look at are the difference between left and right circularly polarized X-rays and how they're differentially absorbed by our sample. And this gives us different spectra. And so what we can see in the home cubane is that we have this sort of derivative-like pattern, whereas in a normal S equals 3 halves molybdenum 3, we have 2 negative features. These 2 negative features we can show computationally largely roughly reflect the splitting of the T2G and EG set. And the only way to understand this derivative-like spectrum that we see in the home cubane and that we assume we would see in nitrogenase if we could actually manage those experiments, is to assume that locally the molybdenum is S equals 1/2. So it's at least experimental support for the idea of this strange non-Hund-like configuration. And this was the work of Joanna Kowalska, one of my previous postdocs, and it was just published late last year. And I should say it was a real heroic effort on her part to get those data. But what I want to show you on this slide, I don't want to go through all of this exhaustively, but this is sort of our current picture of what the active site looks like at the E0 state, right? And so we know it has a carbon in the middle based on valence to core X-ray emission. We also know that the molybdenum has this, and most likely has unusual non-Hund-like configuration. I won't talk about the rest of this today, but we've also done selenium substitution of this cluster. We've done Mossbauer, and also iron XMCD, which I didn't talk about, all correlated with DFT. And so this is sort of our current picture, is that this is largely a ferric cluster, so a 4 ferric, 3 ferrous, with an overall charge 1-. Exactly how these charges are distributed, I think, is still open to debate. But for us, it was really important to define E0, because if you want to calculate a mechanism or think about this experiment, you at least need to know the starting point. Last year, go back to this. Last year, we also published some of the first studies that now look at the E1 state, so just one step beyond the resting state. I don't have time to talk about that today, but I think we're sort of slowly advancing in this cycle. But I chose to tell you the E0 story in part to sort of give you the evolution of how challenging it can be sometimes to identify exactly what the atomic composition is, and then to really understand the electronic structure in detail. Okay, but I'm gonna switch gears now and talk a little bit about methane to methanol conversion. And so perhaps as many of you know, methane is worldwide a wasted natural resource. In Europe, but actually particularly in the US, we flare a lot of methane at remote sites where we're drilling, and it's just not cost effective to try to transport that methane and use it for fuel. We, of course, also generate a lot of methane worldwide from the agricultural industry. And methane, of course, is a really powerful greenhouse gas. So many people say that it has a global warming potential that's about 20-fold greater than CO2. And I think it's estimated that livestock alone contributes about 3.1 gigatons annually to CO2 effective global warming. And so in principle, if we wanted to use this methane and convert it to something useful like methanol, something that could be more easily transported, we need an effective way to do that. And of course, industrially, methanol production is a complex multi-step process, and that's just what I'm showing here. So we use both steam reforming, we use the water gas shift reaction, and typically this needs to actually go over multiple reactors because the process is also not terribly efficient. And so from a fundamental research perspective, we are quite interested in asking, how do I directly do methane to methanol conversion? And here it's clear we could certainly learn lessons from biology, where soluble methane monooxygenases are well known to be able to affect this conversion directly. And so in methanotropes, I should mention you have not just the soluble methane monooxygenases, but also the particulate forms. The particulate are even more complex, so I won't talk about that. We also work on those. But today I'm just going to talk about the soluble MMOs, which contain, again, an iron-based active site. And similar to nitrogenase, this also requires more than one protein to make this happen. And so we're quite interested in the catalytic site. This is MMOH, it's a hydroxylase. But we also require a reductase and a regulatory protein. And recently in the literature, there's been a lot more about MMOD. But one can, ask, since these methanotropes are able to affect this conversion directly, can we actually just use the methanotropes to locally capture methane and convert it to methanol? And this is perhaps nothing that involves my research, I will say, but there actually are MMO cow packs that have been patented. And so they really are cow packs with methanotropes designed to capture the methane produced by a single cow. That's estimated to be around 500 liters per day. And the thought is if you can use these bacteria to affect these conversions, you probably could at least then locally provide energy at remote sites. But as I said, this is pretty far from my own research, and what I'm really interested in is trying to understand mechanism. And so let's talk about what we do understand about this mechanism. And so the protein, as isolated in its oxidized form, needs to be 2-electron reduced to a diferrous species in order to interact with oxygen. Okay, and so this diferrous species interacts with oxygen, and then oxygen binds between those two irons at a peroxyl level, so with an OO bond still intact. What needs to happen at the next step is that OO bond needs to be cleaved, and it forms either this so-called closed iron 4 dimuoxo diamond core or an open core, and this is known as MMO intermediate Q. So we have intermediates P, Q. Q is especially interesting to chemists because Q can directly abstract a proton from methane. And for the chemists listening, this is something really hard to do. And so we would love to know the exact nature of this hot intermediate that affects this very difficult conversion. And so what I want you to just focus on are these two intermediates Q that I showed here. And what I want to emphasize is that these two intermediates would have either an iron-iron distance of 2.5 angstroms if I form this diamond, or if it opens, that distance increases to about 3.4 angstroms. Okay. Now, early EXAFS studies published in the late 90s by Larry Kay's group showed an iron-iron distance of 2.46 angstroms. So this was sort of the first evidence that it might be this closed diamond core-like structure. More recently, doing transient Raman studies, Dennis Proshlikov's group together with John Lipscomb's group did really heroic transient Raman experiments. This is the difference between the 16 and 18 oxygen label, and the black background there is with no enzyme. So you can see that they're looking for really subtle differences. That's why they show these different spectra here. And based on these spectra and correlation to model studies, they indicate there are similarities with the diamond core. This is interesting and no doubt absolutely heroic experiments. I think they needed about 30 grams. I thought it was a typo, but it wasn't. 30 grams of protein to do this experiment. So really hats off to the first author, Raoul Banerjee, who really made this happen. The question we had though was, is this Raman, does it have to be only the diamond core? And because no Raman exists for an open core, that also remains a bit of a question. Okay, so why am I saying that, you know, there might be need for further verification? Actually, I'm just quoting Amy Rosenzweig here, who commented on that article and basically made the comment that further verification of the Q structure is now desirable and might be obtained by high-level computational studies and additional spectroscopic work. And we agreed with Amy in part because there is sort of conflicting evidence in the literature. Larry Kay's group has shown, for instance, from his model studies, that if you take similar models and you go from a diamond core to an open core, it becomes 1,000,000-fold more active for H-atom abstraction. And so if the open core in a similar ligation environment is so much hotter, why wouldn't nature also use that? Okay, so that's one question. The other question is that from theoretical calculations that have been good for predicting intermediates in other biological systems, they were never able to reproduce that very short iron-iron distance from the EXAFS. And so again, my group's question was, can we use some sort of advanced X-ray spectroscopic approach to get new insights? And this is the work of one of my PhD students, Rebecca Gomez Castillo. And so Rebecca used that same Herft experiment I already told you about for molybdenum, but now she's using it at iron. And here you can also see what the setup looks like. So the sample fluoresces, and then she's using a Bragg optic to spectrally analyze that and put it back on the detector. And so here she's showing you her TFY data compared to her Herft data and how much more that sharpens. And the question is what can Herft then teach us about just the structure of different iron dimers? And so what we always like to do is to just sort of correlate to known structures. And so here we looked at iron models that had a bis mu hydroxide, a mu oxo mu hydroxide, or this oxo bridging motif. And so what you can see here are the correlations between experiment and theory, which are generally good. And this kind of just sort of reassures us that, look, these were structures I knew, and so I can use this correlation to understand the structure of something that's not known. And so this is the approach we took. And together with John Lipscomb and Raoul Banerjee, we looked at MMO in its reduced states, so the diiron 2, its oxidized state, so the diiron 3, and then we looked at this Q intermediate. Now, I should explain to you, because it's not always clear to people who are outside of this field, is we're having to trap intermediates here. So red and ox, these are quite stable. That means we can just prepare these proteins and just freeze solutions and measure them at 10 Kelvin so that the beam doesn't damage them. But Q is only formed transiently. And so we do a technique called rapid freeze quench where we mix red with oxygen, and at a given time point, we trap what we have. And then we look at how much Q we have by Mossbauer, and then we use that to deconvolute our X-ray spectra. So here's just an example where we had roughly 30 to 40% Q based on the Mossbauer, and then the rest was some ox and red. And then we can deconvolute it and get this blue spectrum here, which it would be a pure Q spectrum based on the Mossbauer. And I just want to emphasize this because when anyone talks about studying intermediates, it's important not to underestimate how challenging it is to know what you have. And it's really important to try to combine techniques so that you have a more robust idea of what it is you're measuring. And one thing you can really see here is here's ox and red, but whatever this Q thing is, it has a way more intense pre-edge. It also has a much higher energy rising edge. Now remember, this rising edge relates to the 1s ionization energy. So if my iron has gone from iron 2 to 3 to 4, then Q should have a much higher energy rising edge, and it does. So this is certainly consistent with iron 4,4, but then the question is, what is this very intense pre-edge, which is a 1s to 3d transition at the iron? What does this tell me about the local structure around the iron? And so what we can do is we can say, well, does it look like the diamond core? Because the diamond core model exists and we can measure it, and so we did. And you can see, well, this is Q, and my diamond core model is much, much less intense than Q. So we thought, doesn't look that much like that. So how does it compare to an open core model? And so these are, again, Larry Kay's models. And when you open the core experimentally, the intensity of the pre-edge goes up, and the same thing happens in the computations. And so this is some of the first evidence we had that, well, hey, maybe an open core actually is more consistent with the local site symmetry. But let's be clear, the protein environment can further modulate this, and so we are presently completing a QMM study with Frank Naza's group to try to really understand what this local structure of Q looks like. But just based on the information that we know, the arguments for the closed core were that you had this short iron-iron distance from XAFs, although it wasn't reproduced by the synthetic models. The Raman said you had to have 2 equivalent oxygens, which certainly would be true in a diamond core. And also, I didn't mention this, but the Mossbauer argues for 2 equivalent irons. So if I draw the open core this way, obviously it's consistent with my HERF, but how can I possibly make it consistent with the Raman and Mossbauer requirements? And perhaps if I just invoke hydrogen bonding, this could become equivalent, and we could say maybe the open core is sort of equally reasonable. But this sort of led us to the question of, we really need to revisit this short XAFs distance, because that seems to be the major argument for the closed core. And so we wanted to really look back at this and say, look, a closed core has to necessarily have a short iron-iron, whereas an open core necessarily has to have a longer iron-iron. Okay, since I understand that you won't all necessarily be familiar with XAFs, let's talk briefly about what XAFs is. So this is the iron K edge that we talked about, right? So we had the 1s to 3d pre-edge. We had this sharp rising edge when we ionized the 1s electron. Now, once we've ionized the 1s electron to a continuum, we can think of it as a photoelectron wave vector that's propagating out from that photoabsorbing atom, and it'll get backscattered by neighboring atoms. And when that backscattered wave returns, it will interfere with an outgoing wave, and it will result in this oscillatory pattern, which is known as the extended X-ray absorption fine structure. That extended X-ray absorption fine structure are these modulations, and the absorption coefficient is a function of energy. And if you see them in papers, they're most likely presented in K space. So rather than energy space in EV, we basically just changed our unit so that we can express this in reciprocal angstroms. And this is convenient because then when I Fourier transform it, I have a basic radial distribution with respect to my absorbing atom. So if my absorber is iron, you can imagine iron sitting here at 0. And this says I have a lot of things around 2 angstroms and then some more things just above 3 angstroms. I caution you, you cannot read these distances directly from the Fourier transform, but it can give you an idea. The other thing I want to say is that XAFs depends strongly on the nature of the scatterer. So a scatterer like oxygen is not a very strong scatterer, and it won't modulate the signal very strongly. But another metal, which is what we're after, another iron, it has a lot of electrons, it's going to scatter strongly, and it's going to modulate my XAF signal. So here's an example. This is an iron dimer, and this really strong outer shell peak is from that iron-iron interaction. Okay, and so this is something that XAFs is very good at, but keep in mind that XAFs sees the average of all contributions in a sample. And so this is also challenging because biological intermediates, as I already pointed out, are never just one species at a time. And so we realized if we wanted to redo these experiments, we needed more selectivity. And so this was a project of George Cutsales, who's a former postdoc in my group, who's now an independent research group leader at the MPI. And what George took inspiration from was work of Peter Glatzel's and Uwe Bergman's, where they did site-selective X-ray absorption spectroscopy on Prussian blue. So they used these K-beta lines that I already told you about, the 3p to 1s transitions, to separate out the iron 2 and the iron 3 sites based on the shifts in their K-beta lines. And so we thought this would be a cool way to maybe select just for the iron 4 subcomponent. Unfortunately, you can see George is less happy in this picture here. What we found, and I'm also presenting this because this is often the way science happens, we found that MMO red, OX, and Q, although they had different edges, you saw, and they even have different shaped K-beta lines, but for details that I won't go into, they have overlapping K-beta main lines. This has to do with basically canceling effects of changing D count and covalency. So we've since come to understand this, but it meant the experiment we thought was really cool didn't work. And it actually told us we didn't understand something yet. So that's a plus side of an experiment gone badly. But what we did find is that we could look at MMOQ and we could compare it to models that had S equals 1 spin state and see that Q was very different. Q actually is locally S equals 2, it's high spin. And this is another one of the reasons we think it may be more active, but this was a nice experimental fingerprint for the nature of the iron site in Q. But George had to somehow turn this experiment around, and rather than doing the harder K-beta experiment, he went back to those K-alpha lines that I showed you, and he said, hey, look, we've got this spectrometer set up. Let's see what we can do with getting XAFs off the K-alpha. And he measured XAFs of this whole series of reduced, oxidized, and MMOQ. And I have a yellow box here to show you where that peak would be in MMOQ, that short iron-iron at 2.46. And you can see none of these samples have anything here. And this holds for many, many measurements because George had to redo this over and over again to convince ourselves and our collaborators. But what he found is that MMO red, it looked basically like what we would expect from previous XAFs and from crystallography. It had 5 iron oxygens, a little over 2 angstroms, the iron-iron distance at 3.25 angstroms matched, and it also had iron-carbon contributions from backbone alpha carbons. And similarly for OX, he could fit an iron-iron that gets shorter at 3.00 angstroms. Now, what happened for Q in his case, and not surprisingly, because you don't see anything here in the Fourier transform to fit, he wasn't able to fit anything short, but he found a long iron-iron. And so this definitely seemed to favor an open core model. And this is fine, okay, it favors the model we propose, but now you have 2 inconsistent data sets. And this becomes an important question to resolve. How do I resolve what's happening here? And so first we need a hypothesis. And we looked at the data and said, okay, we were comparing our old reduced and OX data and the old Q data. And so all the old data are in red and our new data are in black. And you can see that, okay, the OX looks similar, but there's even some differences in the reduced. And by far and away, the worst looking data here is for Q. Okay, and we had to ask, well, where might these differences arise from? Now, I know this is a lot of details to keep in mind, but remember I told you The reduced and the oxidized are frozen solutions. They're slightly more homogeneous samples. And Q is an RFQ, a rapid freeze quench powder pack sample. So it might also be a little heterogeneous. We'll talk about that in just a bit. But looking at this, we thought, could there be a difference in the background contribution? Now, for those of you who've ever been to synchrotron beamlines, you know they're full of metal parts. And we kind of thought, well, maybe it's some sort of background scatter. But how do we think about this, and why would it be different in the two different experiments? Okay, so I'm just going to take you to the insides of the synchrotron beamline where we are doing this experiment. So you come in with your synchrotron beam, you hit your sample inside your metal-walled cryostat, the sample fluoresces and hits the detector. But the beam also scatters off the walls of the cryostat, and so anything else could also hit your detector, right? There's no spatial discrimination. I don't know that the signal had to originate from my sample. Okay, so what happens differently in George's new experiment compared to the old experiment? As I told you, he has a Bragg optic. And this Bragg optic has to be aligned along a Roland geometry, which means that only the point source from my sample is at the right distance to satisfy that Bragg condition, whereas scattering that comes from elsewhere does not satisfy spatially that Bragg condition. And so it gives you a way to actually eliminate possible background. Okay, this is a hypothesis, but is that happening? Well, first we had to ask ourselves, what would background scatter actually look like? And we looked again at the HERFT and the PFY, and we thought, you know, we have this iron-iron at 2.46, and this is exactly the distance in alpha iron. It also has a distance at 2.46. And if I just artificially contaminate my HERFT spectrum with metallic iron, I can get something that's almost identical to what was previously published. Again, though, we haven't proven anything, right? It's just a hypothesis. So how do we test this hypothesis and how it might have happened? Well, basically, our thought was that if there's background scatter possible, it should vary depending on where I am at my sample. And so we started to do the same experiment that was done in that original science paper. We got rid of the optic, we redid this partial fluorescence yield, and we asked the question, does it matter where I collect my data? And what we saw is we moved to different spots. We got differences in the edge. These are more subtle, but these manifest in actually dramatic differences in the XFs, which we could show was actually metallic iron. And we could also show that if we were really careful about the spots that we picked, so if we eliminated any of these spots that had a rise in the pre-edge, we actually got data identical to the HERFT. So the physics that's happening in these two experiments are not different. It's just a question of identifying what's in the background. And if we really carefully check every single spot and make sure there's no evidence for background, which I will point out is hard to do if you don't know what a subtle effect you're looking for, right? We had the HERFT data to sort of calibrate ourselves. And what I want to point out is this isn't the first time this has happened. So there are many examples actually in the bio and organic literature of anomalously short iron-irons that were found in XFs. And so what we think may have actually happened, unfortunately, is as the samples get more dilute, as you have these rapid freeze quench inhomogeneous samples, you simply become more susceptible to these small background effects, especially because you're probably having to average over hours and hours, and something that you wouldn't see in a blank does show up after 12 hours. And this is one of the challenges of the way synchrotron research is done, and the fact that we often don't have the luxury we have in labs to do all of these checks. And so this is just another example that if you don't even look at Q, but you look instead at MMOH ox, in a solution, it's relatively insensitive to background, but if we take an oxidized sample, so not the intermediate Q, but just regular ox, and we rapid freeze quench and have a powder version of that, then that sample in her heterogeneity makes the background more sensitive. And I want to point out that another way to get around this would be to just simply have more concentrated samples, if that's possible. But in biological samples, that isn't possible. But there was a group at Penn State who showed that if you use higher concentrations, you can also eliminate some of these background issues. And so there, I just want to sort of conclude by saying we have HERFT and XAS data that support an open core structure. We're still trying to understand the Raman, but we do have calculations that certainly suggest that even the 690 wave number feature very well is consistent with some of the open core models we've generated by QMMM. And so I hope that I've been able to show you that X-ray spectroscopy provides us a unique elemental selective way to look at geometric and electronic structure and these complex cofactors, and that we really need to keep pushing instrumentation and methodology in order to further understanding, not just in biology, but I think in catalysis in general. And with that, I will thank my group once again and thank all of you for your attention.
Thank you, Serena. It was a nice talk. I think we have one or two questions here in the chat box. Sunita?
Yeah. Thank you, Professor Serena, for the nice, wonderful talk. Right now, we have one question. It's from Dr. Bhavani Narayan from St. Joseph's College. Does Fe2 plus 2.5 plus in the current picture of E0 state of FeMOCO depict Fe shuttling between +3 and +2 oxidation states? What is the best tool to capture and identify an ion oscillating between two oxidation states if the kinetics of the oscillation is pretty high?
Yeah, so I should point out that you know, that's really a sort of schematic drawing based on a broken symmetry DFT. So by no means do I mean to imply that it really is iron 2.5, 2.5. I think that that's something we can most readily assess in iron dimers. And in that case, Mossbauer is probably one of the best tools for us to look at the extent of delocalization, right? And to look at whether or not it's really a localized 2,3 or a fully class 3 delocalized 2.5, 2.5. In that case, for an iron 2,3, you would obviously have these separate doublets, and in the truly totally mixed valence, those doublets would collapse. I would argue, though, in a cluster as complex as FeMOCO, it remains challenging to say exactly where those mixed valent pairs are. I've simply showed computationally where they appear.
Thank you, Professor Serena. There is another question from Vishal Kamath. He has not mentioned his organization, so I cannot tell that right now. He is asking from YouTube, message he has posted, why does MO +3 have different electron distribution as compared to normal distribution of electrons?
Yeah, sorry if I didn't make that clear. So normally molybdenum 3 is D3, and you're completely right, it should look like this. There should be 3 electrons all with the same spin orientation so that it's 3 halves. What we believe is happening is that this unusual spin flip happens because the molybdenum actually has bonding interactions with the iron. And so in a simple picture, we sort of think of it as a mixed valent pair that has the same spin orientation as each other that interacts with 2 of those electrons, and then an isolated ferric site that interacts with the others. Again, as I said, this is an experiment that's done in the computer, but what we can do is we can replace those irons with something closed shell. And when we replace the irons with something closed shell, the molybdenum goes back to a normal 3 halves configuration. And so that's at least a computational experiment that is consistent with molybdenum iron bonding favoring that unusual spin flip. As I said, our only experimental evidence or experimental data that suggests this may be the case is the molybdenum XMCD.
Thank you, Professor Serena. Okay, there are no further questions to my knowledge.
Okay.
I'm giving it to Nalini ma'am to take it forward.
Sure.
Hi, Serena. I have one question, just an experimental one since you use the synchrotron. What was this one? How is the sample actually prepared there? Actually, like in the sense, is it a powder? What is it?
No, so for most of our protein samples, they're dilute solutions. So they're typically on the order of about a millimolar in the absorber, and they're biological, so they'll be in a buffer, and then it's frozen and measured at 10 Kelvin because most of these biological samples will damage quickly in the synchrotron. For the intermediates we trap, they are rapid freeze quench powders. So we start with a solution and we end up with a snow that we have to pack into a cell.
Sorry,
yeah.
Go ahead.
Oh no, so the snow, because we can't homogeneously pack it, that we think is part of the reason we had more background issues, like for the Q samples.
Typically, HERPRED measurement takes how long, like in the synchrotron?
It really depends on the concentration. So probably for many of the samples that we're measuring, it takes hours. But for concentrated samples, it could take minutes. So it.
Okay.
Yeah.
But the protein has to be shouldn't be denatured by it, right? You don't want the biological sample to be denatured.
No. Yeah. So we spend a lot of our synchrotron time actually doing damage studies to figure out how much X-ray dose the protein can take before it starts to show signs of damage. And in many cases, like for the MMOQ samples, we could only expose the protein for about 30 seconds per spot. And then we have to raster in order to collect full data sets. So it's challenging for the people who are doing this, yeah.
Yeah. Okay, thank you. Any other questions here?
There is one question, Nalini, for Professor Serena. It's how does she exclude any rapid beam damage in her sample? It's from Bianca from Karlrath's Institute of Technology, Germany.
Okay. Yeah, so that was actually in part what I was just answering to Nalini. We spend a lot of time doing damage assessment. And so what we're looking for is how long we can spend on a spot before it damages. Now, if the sample doesn't change at all, we don't know if it didn't damage instantly. And so to address the question of whether it damaged instantly, we will often attenuate the beam with filters so that we reduce the flux until we can verify whether or not it would look different at lower flux. And so typically for samples that we're not familiar with, we'll spend at least several hours doing these kinds of assessments. Yeah.
Any other questions, Sunita?
Thank you, Professor Serena. Right now, there are no questions.
Okay.
Yeah. So I have just one last comment. We have a lot of undergraduate and postgraduate students who are also attending this seminar, this talk. Okay. So is there any way that you can tell them how this X-ray absorption spectroscopy and XAFs, how it really, I know you put one slide where you showed the difference, how fine structure can be gotten. Like 2 or 3 lines, can you just tell them how different it is, like with respect to how you can get the fine structure from the X-ray?
From the XAFs region, or?
Yeah, generally how XAFs is really a specialized technique.
Okay. Yeah, so I think, unfortunately, I should have maybe put more slides in on XAFs. So as I was saying in my talk, the XAFs results after the electron has been ionized to the continuum. And so we approximate it as a photoelectron wave vector that is propagating out and is backscattered by neighboring atoms. And so what happens to that wave vector, right? So we can, from scattering theory, we can approximate that as an exponential function that becomes modulated by the phase and amplitude parameters of a backscatter. Okay, and so if we basically have an outgoing photoelectron wave vector and a returning photoelectron wave vector that are modulated by phase and amplitude parameters of the backscatter, I can mathematically transform that by Euler's theorem to get a sine wave, okay? And so that is this beat pattern that you actually see. And within that sine wave, then we end up with an expression that depends on the coordination number, the distance, and the disorder, okay? And so this is really hard without a chalkboard.
No, that's fine. I mean, just because a lot of us are chemists here.
Yeah.
Yeah, and so we always think in terms of metal distances, metal, bonds, a metal oxygen bond, and so that's why.
Yeah, no, I mean, I think it's a beautiful thing with excess. I mean, its ability to extract the distances once you have this expression is quite accurate. So on the order of 0.01 angstroms, which I think is quite nice. The problem, as I said, is you see the average relative to that photoabsorber. So if you have both oxygens and nitrogens that are similar scatters, those will group together and they'll contribute to the same wave. And that's the challenge in terms of getting very precise structural information, because you often don't know the wave that you see, what exactly to attribute it to in your sample, but you will get a very accurate radial distribution from a family of backscatters, of similar backscatters. Yeah.
Okay, thank you. Ronald, sir, do you want to say a few words? Or sir, you're muted, sir.
Yeah, you can proceed with the vote of thanks.
Yeah. So Serena, thank you. So I'm going to do the vote of thanks. I'll just share screen with the thank you slide. So that, 1 minute. Sorry, 1 minute. Yeah. Okay. Yeah, I would like to I would like to read out the vote of thanks. Thank our speaker first. So, ladies and gentlemen, that was a very nice talk. And on behalf of all of our principal, the management, our HOD, and faculty of the Department of Chemistry of St. Joseph's College, I would like to thank our speaker, Professor Serena DeBree, for this informative and interesting webinar on X-ray spectroscopy as a tool for understanding biological catalysis. So you can all applaud, you can give a hand. So here, what she actually started with a very, very simple premise as to how to harness energy in chemical bonds. So it was a very, very important question in chemistry, and she emphasized it with two reactions. One was the reduction of nitrogen, and another one was oxidation of methane. So using these two reactions in biological processes, she walked through the fascinating story of how X-ray spectroscopy, that is using XRF or HERREP, synchrotron, that is which are used in synchrotron techniques, how they help in understanding the electronic structure, the oxidation state of these catalysts, and how they can be mimicked in real life reactions. Okay, so these are the two things that she had very, very explicitly explained. Yeah, a little bit of very, very sophisticated techniques were also taught to us. Some of the names I'm also listening to for the first time. I'm sure for our undergraduate and graduate students, it must have been a little bit complicated, but it is very nice to know that these techniques can be used for finding out the oxidation state, the charge, and other electronic structure requirements, which will help in answering bigger questions in chemistry and biology. So it was really a pleasure. First of all, I should say that it was a pleasure interacting with her. After a long time, I just because Ronald sir was very particular, I touched base with her, and she really interacted very fast. So it was very nice. I'm very grateful that despite that she is on vacation, she was able to give us some time and also adjust her timings to address from a different time zone. So thank you very much, Professor Serena, for this. The organizing committee keeps on record a gratitude to our principal, Father Dr. Victor Lobo, SJC, for his encouragement and support to conduct these webinars. My heartfelt gratitude to our HOD, Professor Ronald Mascarenas, for his continuous support, guidance, encouragement, and also heading the organizing committee that of this international webinar, which consisted of Dr. Libby, Dr. Joyce, Dr. Suhas, Dr. Jayashree, myself, Dr. Sunita, Dr. Rashmi, Dr. Palraj, and Dr. Suryanarayana from the Department of Chemistry, St. Joseph's College. I appreciate this teamwork and thank all of them. I'm also thankful to special thanks actually to Dr. Suhas and Dr. Jayashree from the Chemistry Department, because they took care of the technical aspects of this webinar. That is live. This webinar has been live streamed to YouTube, and this would not have been possible if Dr. Suhas and Dr. Jayashree have not worked on it. I would like to express my gratitude to all the participants of this webinar from our college, from other institutions, research labs and industries from India and across the globe for attending this webinar. Thank you very much to one and all. Again, thank you very much, Serena. It was a very, very nice and informative webinar. Thank you.
Thank you very much for the
Yeah,
invitation.
thank you.
Yeah,
Thank you,
we'll be in
Professor
touch.
Serena.
Yep.
Thank you very much, Professor Serena, for that excellent talk. So we shall have more such talks.
Yeah. Great. Thank you very much.
Thank you. Thank you. Yeah.
Bye.
Bye. So, just leave the meeting.
Yeah, we will sign out.
Yeah. And you want to meet? Yeah.
We can meet on meet some other time.
Okay. Thank you, sir. Thank
Yeah,
Can
you
I
very
leave the
much.
meeting, sir? Can I leave the meeting,
Yeah.
sir?
Excellently done, all of you. Thank you so much.
Yeah.
I will
Yeah,
just leave it
Jayashree.
and then I'll leave, sir, now.
Yeah.
Yeah.
Yeah, we're
Thank
leaving,
you.
sir. Thank you. Thank you.
Thank you, all of you. Yeah. Thank you.
Sir, I will end the meeting.